Lab 2, Motion of a Falling Object. The purpose of this lab is to create different computational models examining the effect of forces acting on an object in free fall. The lab once again addresses Newton's second law, given by these equations. In this lab, the net force on the object is non-zero, therefore the object will not travel at a constant velocity. The two forces we are going to examine are the gravitational force acting on the object by the Earth and the drag force on the object due to air resistance. Here is an outline of the steps taken throughout the lab. To begin the lab, I took a video of a crumpled piece of paper being dropped from rest. Before beginning the analysis, the diameter and mass of the ball were inserted into the program. The system was identified as the ball, and the coordinate axes were established with the negative y direction pointing down. These initial conditions taken from Tracker will be used in a computer code to create computational models of the object's motion. Looking at the code, the mass of the object was changed. The initial position and velocity vectors were put into the code based on the initial conditions found in Tracker. The magnitude of the acceleration due to gravity was established. The j-hat unit vector was also established in the positive y direction in order to match the predetermined coordinate axes. The proportionality constant of drag was determined. However, when only analyzing the motion of the object due to gravity, this was set to 0. The while loop was edited to run only through the final time of data collection. Here I set a variable called speed equal to the magnitude of the velocity vector. I then set the force of drag equivalent to this equation. Notice that the drag force is in the opposite direction to that of the velocity vector. The force of gravity was established in the negative j-hat direction. The net force was set to include both the force of gravity and the force of drag. Lastly, these two equations were updated to match Newton's second law. The largest difference between these two models is the visual representation of the drag force given by the blue arrow. However, the graphs of these two models look extremely similar, therefore we need to put the two data sets in one graph in order to properly analyze the data. Looking at the graph, we can see that the model only exemplifying the force of gravity overestimates the position of the object. Looking at the equation set forth by Newton's second law, the net force is larger than that of a model that includes drag, therefore the position of the ball at each time step increases. The model including drag more accurately represents the actual motion of the ball analyzed by Tracker. With a force included that opposes the direction of the gravity force, the predicted position of the ball is much less than that of the gravity model. Notice that the last data point is where the paper ball hit the ground, therefore this data point can be ignored. The what does it mean question asks if either model predicts a terminal velocity. First off, terminal velocity is the maximum velocity that a free-falling object reaches. This is only achieved when the net force on the object is 0. The gravitational model does not predict a terminal velocity. If there is no force opposing the force of gravity, the object will theoretically continue to accelerate until it hits the ground. On the other hand, the motion of an object including drag will predict a terminal velocity. By setting the net force equal to 0, the terminal velocity can be mathematically predicted. However, when examining the y velocity outputted by our code, the object never reaches its calculated terminal velocity. The what if question asks if the terminal velocity would be different if the object were initially thrown downward instead of dropped from rest. We can mathematically prove that the terminal velocity would be larger if another force were to be added to our net force equation. As you can see, a larger force downwards will lead to a larger terminal velocity. If we were to set an initial velocity in the negative y direction in our drag force code, we can see that the ball reaches a velocity greater than what was originally calculated to be the terminal velocity. Therefore, an initial force from a downward throw would increase an object's terminal velocity. Again, the gravity model would not predict a terminal velocity. Here you can see that as time increases, the final velocity will indefinitely increase regardless of an initial velocity. To conclude, Tracker was used to obtain observed data of an object in freefall. The data obtained from Tracker was used in a GlowScript code. These codes were then used to create computational models and sets of data for both situations. These sets of data were compared, only to discover that a model not including drag will overpredict the position of an object in freefall. It was further discovered that a model taking drag into account accurately predicts the motion of an object falling in real life. Lastly, it was discovered that a model only taking into account gravity will not predict a terminal velocity. Newton's second law was utilized throughout the lab because it accurately predicts and explains the motion of an object experiencing a non-zero net force.